All right. The first thing I wanted to do was to show you the word. Okay. George is waving his hands. To show you the word CB here, which stands for C Blue Words, and the word QWERTY, which is the QWERTY keyboard. And I'm going to move the cursor down to the word CB and activate it, change it from a comment into a executed word. And the reason I'm going to do that is so that you can see the blue words. Now, I see the blue words whether they're visible or not, because they execute. So I know when I see a line end and another line begin that there was a carriage return there in blue, because originally Colorforth just jammed everything onto the screen until we added blue words that execute at edit time and let us rearrange the look of our code to make it work better. And likewise, the word QWERTY there is a comment. And I just wanted to make a little observation about that. I had an interesting experience recently, which was that I had the QWERTY keyboard turned on, and I started using Colorforth, and I didn't realize I was doing it, and it worked just fine. And this doesn't sound odd, except that in order to learn the quasi-Dvorak keyboard years ago, I had to kind of block out the part of my brain that attached my fingers to a QWERTY keyboard. And that block was always in place when I was using Colorforth. So when someone added the QWERTY keyboard into Colorforth to make it easier to use, this really made it hard for me, because my fingers wouldn't go into QWERTY mode when I was doing Colorforth. And then one day, somehow that block just kind of went away, and I was doing Colorforth with the QWERTY keyboard on, and the part of my brain that had been blocking that part of my normal coordination was unblocked, and so I could proceed. And I make this observation because I think there's a lot of things like that about Colorforth, that you have to block out some stuff you already knew about other kinds of forth, or some stuff you already knew about other environments, before Colorforth starts to make sense. And when you block that stuff out, it's easy to learn Colorforth, but if that reflex is active in your brain, you might have trouble making sense of what Colorforth does. So what I wanted to address today was how we use the tools to actually do applications. And so the first thing you have to do is you have to edit some code. And as was always the tradition with blocks, you put a block number on the command line and enter it and type edit, and it takes you off to the editor. Oh, I'm in the wrong system, aren't I? Oh dear. Okay. Just a minute. Let me remind myself of what I'm doing. Okay. I think I had what I'm going to do is just close this and start up with a Colorforth. And I'm going to maximize it to the size of the screen, and I'm going to check some documentation, and then I'm going to go to block 830, and that's not the one I wanted to edit. Oh my, what am I doing? 840. Okay. Here's a block where I can enter some code if I want to write a program. So what I'm going to do here is I'm going to write a word, and we'll call it demo. And we'll do something very simple, the simplest sort of thing that one can do. We will bring a pin high. So I've gone into hex mode and entered a number with the two most significant bits high. If I output this to the IOCS register, it will turn one of the pins on. The two bits mean output and output high. So if I put that number on the stack as a literal, and then store it to where the B register points, which is by default the IOCS. That's going to raise a pin. Oh, thank you very much. I typed it backwards. Store B. Okay. Store using the B register as a pointer. The B register defaults to pointing to the IOCS register, so this code is going to send that number to the IOCS register. And now let's put a little delay in here. Put a number on the stack. Do a for next. And then just to be nice, let's put a carriage return in blue and put this on another line. And now let's output 20,000 in hex, which is going to turn that pin on bit 17 low. And we can send that to the IOCS register, and we can put in another number, not in hex. We'll just use 100 like we did before, and we will say for next to give us a delay, and then we want to loop back to the word demo, and the easiest way to do that is to call the word demo, and then put a semicolon after it that turns that call into a jump. So now we've got a closed loop. Takes 30,000 hex, sends it to the IOCS register, delays for a while, sends 20,000 hex to IOCS, delays for a while, and loops. Yes? All right. When I'm using the QWERTY keyboard, you will see that these are the keys that are under fingers. And I prefer to use the the Dvorak keyboard because it's less movement for your fingers. It's faster, it's easier. When I hit the E key and go into edit mode, these are the keys that the editor has assigned for moving left, right, up, and down, changing colors, red, green, magenta, cyan, yellow, for toggling the color of a word. We'll show you more of this later. Meanwhile, when I enter a word, such as if I type the word D-E-M-O, you'll notice that I get a binary number. I get a hex number over there. Actually, it's not hex because I'm not in hex. But I get a number which is the representation of that string, and you see the string on the command line. And if I hit a space bar, it'll try to execute it. If I enter a number, 1, 2, 3, the number appears there. In fact, that is a view of the stack. You don't always see it, but you always see it when it's there. Sometimes it's not there in certain programs and you have to remember, but other times it's there and you can just look at it to remind you what your fingers are supposed to be doing. Okay, you'll notice that there's a 9 here. If I hit, that's the space bar. If I hit the space bar, it goes into number mode. You'll notice there's now an F here. If I hit the Alt key, which is what that represents, we switch to hex mode. So I can enter a number in hex, I can enter a number in decimal. But it's a number. I can't enter a word in this mode, only a number. Meanwhile, if I get out of this and go back to it, you'll notice there's an X over the Alt key. If I press that, I get an alternate keyboard. This allows me to enter number characters as part of a string, as part of a name. This isn't a number, this is text. And these are extended text characters when you want to use a semicolon or a comma, or very infrequently used characters like Z and J. Because they are not used as often as the keys that are under the fingers you use most frequently. Years ago, one of the optimizations Chuck put into Colorforth was automatic tail recursion. If you put a semicolon after a called word, instead of calling that word, using a location on the return stack, then returning to a return instruction to then return, you eliminate one call level on the return stack and one return from the execution by having the semicolon modify the call to demo into a jump to demo. And the reason that this was done was this was the simplest form of to make a word recurse back to its own name, because it's not smudged, so you can call it before you get to the semicolon. Semicolon does not switch from compile mode to interpret mode. It doesn't unsmudge. It just compiles a semicolon, or if it's following a called word, converts that word into a jump. Okay? So there's a program. Now, you saw it only took a few seconds to type in my program, and this is the sort of thing that they would show in an introductory programming class to newbies working on a microcontroller of some kind. And if I hit the word C, it will clear the junk I left on the stack. You'll notice we have a stack window, we have a command line, and we have a display of a block. And I'll talk a little bit more about that later. But I can exit the editor here, and I can type SO. Now, let's see. What have I done here? Let me go back to my editor here. Okay. Now, we've got a program, but we haven't told the computer where we want to put this program. So let's go into yellow, put a node number on the stack, sorry, back into the editor. I was in the editor. Look at my cheat sheet, sorry. I was distracted here. Okay. 715 is the node we're going to use, and so we say 715 node. Then we have to tell the compiler where to put our program, and we'll pick location 0 in SRAM and say to put our program there. So now we've got a program that we wrote. We say we want to run it on node 715, and we want it to run in location 0, and you can see the word demo should be located at 0 in memory. So now if I type SO, that stands for soft sim. And thank you. I'm still in the editor. Yes, indeed, I am. Let me go back into the editor, remove that junk, exit the editor, and type SO. And we pop into a version of SoftSim. I can use the commands here to move my viewing window and my memory window so I can see node 715. So let's do that. I'm going to go right, right, right. You see the little red X moving, and up, up, up. And when I get to 715, you see 715 is red here. You see we have a memory dump. You can see from our memory dump, we have a fetch B, fetch P, that's literal, store to the B register, 30,000, then a fetch P, 64, that's our 100 in decimal. Then our 4, next loop, 4, compiles a push, aligns next to the beginning of a word, next is a branch back to here while decrementing our 100, and then we're going to fetch P 20,000, store that to B, then we're going to fetch 64 again, we're going to push it, we're going to go around next, and when we're done, we're going to jump back to 0. So there's our code. You can see it in SoftSim. And now I'm going to move my hand up to this one, and I'm going to go, sorry, I'm going to move my hand up to this row, and I'm going to go up, 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 and right, whoops, wrong, got to pay attention to where my hand is, and we'll go right over there. And now our big array over here shows node 715 right here. And we can see the registers on that node, and we have a view of the memory on that node, and we have a view of that node stacks over here, and we have commands for go, single step, and fast. So let me just hit S for single step and see what happens here. I'm sorry, what was that? Oh, you're right. I forgot something, didn't I? Okay, let's go back to here, look at my cheat sheet, and you'll notice after I have compiled the word demo, I can tick the word demo. Sorry. Tick, demo, boot. And that sets the boot address for this node to the word demo that I just defined. And now I can pop back in. Oops, get out of the editor first. Go back into SoftSim. And now we're looking at node 715, where we've got yellow as the next thing to execute. When I hit the S key, it's going to take 3 cycles to fetch the memory location. And you can see the red is the word we're executing. The yellow is the pointer for where the program counter is now pointing. You'll notice if I hold down the S key that we see the return stack is being decremented from 100 down, and when it gets to 0, we will continue on to the fetch P, store B for 20,000, and we can hold this key down, and this program will just slowly go around this loop. Now, one of the things that you will notice is up here, you see that the node in question is executing our program, and you'll notice that it shows that it has a pin. And it shows that when I write 30,000, that pin goes to a 1, and when I write a 20,000, that pin goes to a 0. And I can get a fairly rough estimate for the speed of my program based upon the numbers there. It won't be accurate to the picosecond level, but it'll do pretty well. And if I hit the G key, it'll just run through there displaying every step. If I wanted to, if I have a big delay in there, and I want it to run faster, I can increase the speed for each step, such as how about 200 per step, and now when I hit the go key, it's going to only display every 200 steps. So we're going to cycle through there, and you'll notice the 1, 0 is toggling very fast because we're actually looking at it faster than it's being toggled. So anyway, that's how you would use SoftSim to compile and run a small program and look at the results in SoftSim. Now, any questions on that so far? Yes. Yes. Well, a lot of things that's the way things look in ColorForth. Again, this is the way Chuck implemented this system, was higher addresses should be higher on the screen than lower addresses, which are lower on the screen. This may not be what you're used to, but once you get the block out of your mind that it has to work that way, it seems just as logical, if not more logical, to put higher addresses at a higher location. I will say, I noticed on this version of the simulator, the words here, which used to be LUDR, left, up, down, right, left, up, down, right, left, got changed, and up became higher, and down became lower. Okay, but that's the idea, is that in our memory dump here, we're showing you memory with higher addresses higher on the screen and lower addresses lower. Same thing throughout these tools. Okay. Because I edited the block that I knew it was going to compile. Yeah, it's set up. There's a screen which defines where it's going to go, and I looked at it and said, okay, it's set up to use that. So, just a load block, yeah. Just somewhere it says, and when you first boot up this system, it'll define a number of words such as SoftSim, and the definition is just go out and load this block where the source code is, and then you're in SoftSim. And basically there's a whole bunch of tools in ColorForth that are defined when you boot up that way as load this block, this name loads that block, this name loads. So when we say SoftSim, it's going to load this, and one of the blocks it loads tells it what to do and where to load the source code. It loads the compiler and interprets source code as target code rather than regular ColorForth code, and that's what I edited and put in and showed you how you would set it up and run it. Now, if we, apparently I was pointing at the close button and closed it by mistake, as one can do in Windows if you're not paying attention. So let me find it again and bring it back up. And apparently I did not save my demo. Okay. Now, let me just say that the SoftSim is available now for download, and it's usable to write programs, learn how the opcodes work, study what's in the ROM libraries, experiment with the code, figure it out, and write real applications and get a certain amount of it done without having any real chips to play with. I've been talking longer than I realized. Okay, quickly here, let me go over to a different version of OCAD, which is set up with an IDE for this board here. And there's going to be more explanation of this later, but again, now I'm talking to a fourth chip down here in a socket on a board. I'm talking it through the interactive interface. This screen shows me a view of what's on the stack. It shows me the path to the node I'm talking to and lets me dump RAM or ROM. And if it's working, I can take a number and say lit, and that number will suddenly appear as the top of the stack on that target processor. So I just did a literal load by putting a number on the PC and then typing lit, and it loaded it onto my stack on the target system. So you can see the top of the stack is now 1, and if I say hex 30,000 lit, I now put 30,000 on top of the stack of the fourth running on the target chip. And now if I type store B, in this context, that is an executable command that's going to run on the target and have it execute a store B command. And since the B register is pointing to IOCS, it's going to take that 30,000 and send it to IOCS, which turned on an LED, or actually raised a signal on a pin that you can see on my scope. If I'd have brought in a PC scope, we could have put it on the screen and fought over what got displayed, but you can see it here if you get close enough. Also, if I type the command $RAM, it will dump the contents of the RAM for this node. And you may recognize this as what you were looking at before. We load a number, we send it out, we delay in a loop, we load another number, we send it out, we delay in a loop, and then we branch back to 0. So we know what this program does. And it was automatically loaded in memory of this node because that's what I specified in a setup block, which I can show you. And now I can put things on the stack, I can look at the stack, I can execute individual words, just like an interactive fourth, and I can launch code. If I say 0, 0 is now on the color fourth stack. If I say call, it will send a command to call the program residing at 0 over to this computer. And presumably, if that happened, there is now a square wave running on the scope here, and it's running at just about 1 millisecond per half wave cycle. So we can go to our program, and I've forgotten which computer I'm working with, haven't I? Where was it on here? I have to look. I have several different things loaded. 1528. Okay. There is the program that we were just running. You can see that with 100,000 4 next loops, executing a word of no ops, and then a next, the timing is just about 1 millisecond per half wave there. Now, if we wanted to fine-tune that, we can obviously subtract our loop time. These are 1.5 nanosecond instructions, and a word load is about 5 to 6 nanoseconds, so you can say we'll execute those 4 in 6 nanoseconds, and this in another 5 or so. So this is something like an 11 nanosecond loop, and we're going to execute it 100,000 times. If we want to make it nanosecond and a half slower, we can drop a extra no-op in here. If we want to make it a whole loop slower, we can put in a bigger number in our loop counter. And in fact, that bigger number there would compensate very nicely for the fact that there's a branch in this half of the loop. It's like one more pass through the loop. Similarly, if we want to speed it up even more, we could take this, turn it into a comment, and put a micronext in here, which would just branch back to the word in which the micronext resides. So now, instead of an 11 nanosecond loop, we have a 2 nanosecond loop. So we're going to need a bigger loop counter in there. In fact, we can't get a millisecond out of one level of micronext looping because it's too fast, but it allows us to adjust the timing at 2 nanoseconds per step. Meanwhile, we can slip a 1.5 nanosecond instruction in and take a 2 nanosecond instruction out and adjust down to a 0.5 nanosecond by doing things like that. Also, if we wanted to make this run much slower, we could put a fetch B drop in here instead of no ops. And now we've got a register access and a drop inside of our loop, so we're adding several more nanoseconds to the loop. And if we want to add more, we shift the fetch B towards the end of the loop. Now the fetch B is still taking the same amount of time, but what's happening now is that there are 2 instructions after the fetch B where it can begin fetching the next word. Well, we can't use micronext with this, so let me take that out. So by moving this no-op from the end of this word to the first part of this word, we have delayed when the fetch B takes place. We've left only 2 words after the fetch B for the prefetch of the next to take place. So again, we have added a delay not only by the fetch B itself, but because it's a memory access, we are no longer starting the prefetch of the next. By the time, it will not be ready when we get there, and it will now take a little longer. And again, if we move So by adjusting where a no-op is, forward or backward, or changing a no-op to a fetch B, we can make adjustments of a nanosecond and a half. By changing the number of micro next loops, we can make adjustments of 2 nanoseconds at a time. So we can fine-tune these things down to a fraction of a nanosecond and get some very reliable little routines out of this stuff. Now, if you wanted to make this run faster, we could put the 3000 3003 and the 2002 outside of our loop. And we can define a new word here, test. And now we could, instead of doing a literal load each time inside of the loop in order to load the number we're going to send, we would do an over, store B, and then let's put the no-ops back just the way we had it. And then for this one, we will do a dupe, store B. So we've eliminated the literals from the inside of the loop. So now our loop can run much faster. Let's say we want to really speed it up, and we don't want to waste a lot of time in those 4 next loops. So we cut them down, give them a count of 0, which means we'll go through that loop once. And now we've got a program which has still got 2 literals in our loop, but the literals are 2 of the literals have been taken out of the loop and have been replaced by stack instructions, which will make the loop run faster. So now we're going to loop not back to the word demo, but to the word test. And we go into SoftSim. My goodness, that's rather odd. Wonder what I did wrong with that. Oh, I'm sorry. Oh, yeah, that's right. This is an old SoftSim. So what I just wanted to show you here was now, if we take this same code and run it again in this system, and the easiest way for me to do that right now is just to restart it, which is what I will do. And if it comes up, oh, I probably should have hit reset first on my machine. Let's see if we're talking to it. We are. By going 1 lit, I can see I put something on the stack. So let's do a 0 call and see if we get a faster loop running on the scope. And you can see it's running much faster now. In fact, we can run a lot faster than this scope. This scope is only 20 megahertz, and we can trim this loop to faster than 100 megahertz. To get it to run faster than 100 megahertz, what we would do is, let's see if I can figure out where I had it on this demo. Oh, that's interesting. Sorry, I'm looking at something other than what I thought. All right. Where did I? I lost my place. Oh, that sounds right. 1330. Okay, there we go. Now, if we wanted this to really go fast, we could remove the over here and remove the dupe here. And we could fill up the stack ahead of time. Whoops, sorry. Yeah. Yeah, the compiler would have caught that if I didn't catch my typo. So we've got 2 things on the stack, 3, 4, 5, 6, 7, 8. Let's put 2 more on there. Okay, so now our stack is filled with 30,003s, 20,002s, and we can just keep sending those off. Yeah? Yeah, well, that's not, we're going to go there next. Okay, so now you can see that we've made this thing run even faster still, but we can obviously make it run faster yet by going down here and commenting out our delays. Okay, so now we have got a loop which has store B, branch back to the beginning, and we can make that faster yet. We make that faster by saying, because a branch is a memory instruction, and we can say begin, and get rid of our branch here and turn it into a micro next. Whoops, I mistyped a word, didn't I? Green. Begin. Okay, we got two begins, and now at the end of our loop, we're going to put, we're going to put micro next. Okay, so now this word basically has store B, decrement the return stack, and loop. And when the return stack gets to 0, it's going to turn it into a -1, and then it's going to fall through into the next micro next, which is also going to decrement the return stack and branch back to the beginning of the same word again. So in essence, this is an infinite loop. And it's an infinite loop which doesn't end in a memory access, but ends in a 2 nanosecond branch. So we basically have got something here running in under 10 nanoseconds to do that toggle to the pin that we saw before. Oh. Okay. Any questions on what I've shown? Okay. Thank you very much.